We're going to find the area of polar graphs, and this is actually a lot easier than it looks. So when we find the area of a rectangular graph, we usually divide into rectangles. But since this is a polar graph, it makes more sense to divide it into slices of pie, like this. And then when we think about how we would add up all the segments of a circle, we usually take the part of the circle and set up a proportion, and we do the same thing here. So that's going to be delta theta over 2 pi, which is the whole circle, times the area of a circle. Now, at first, this looks like it would only work for a circle, but that's not the case. It actually works for all polar graphs. Let's take a look at the graph of r equals cosine theta, which is different from a circle at the origin. So if we were still to divide it into segments of pie, or pizza, like this, it will still work because each segment is part of a circle. It might not be this circle, but you can see that this segment could be part of that circle, for example. And the same thing is the case with r equals sine 3 theta, because if we divide this into these petals into segments, each one can also be a part of a circle. And so this formula for finding area will work for all polar graphs regardless of them. So now we want to turn it into a summation because you're adding all the segments up. And then since we have a d theta here, we can just turn it into an integral. And it's an indefinite integral because the limits depend on the period of each individual graph. So overall, this is the integral that works to find the area of a polar graph.